The observable universe contains somewhere between 2 trillion and 20 trillion galaxies. Here is every type of galaxy, explained in full. Let's break this down. Spiral galaxy. The most familiar galaxy type in popular astronomy was also the most structurally sophisticated. The pinwheel-shaped systems, whose flat rotating disks, prominent central bulges, and sweeping arms of gas, dust, and young stars had made them the dominant visual vocabulary for what a galaxy looked like in everything from scientific textbooks to science fiction concept art. The Milky Way galaxy, where Earth's solar system is located, represents a spiral galaxy. The specific detail that every human being who had ever looked up at the night sky had been living inside a spiral galaxy for their entire life, looking out at the universe from within the specific structure being described here. Spiral galaxies are flattened, rotating systems with pinwheel-like arms of interstellar material and young stars winding out from their central bulge, the rotation being the most mechanically significant single property, the galactic disk spinning at hundreds of kilometers per second, with the spiral arms being not fixed structures but density waves whose pattern rotated at a different rate from the actual matter within them, the stars moving through the wave pattern rather than being permanently attached to specific arm positions. The arms and disk of a spiral system are blue in color, whereas its central areas are red like an elliptical galaxy. The color difference communicating the two different stellar populations present within the same galaxy. The central bulge dominated by old red stars whose star formation had largely ended billions of years ago, and the disk and arms populated by young, hot blue stars whose formation was still actively ongoing wherever gas clouds were dense enough to collapse under their own gravity. Normal spiral galaxies are designated S in the Hubble classification system, with the lowercase letters A, B, and C indicating the tightness of the winding and the size of the central bulge. SA galaxies having tightly wound arms and large bulges, SC galaxies having loosely wound arms and smaller bulges, with SB as the intermediate. The Milky Way was classified as a barred spiral rather than a pure spiral, but the spiral structure was the dominant visual element that connected Earth's galaxy to the broader category. The Andromeda Galaxy, M31, the most distant object visible to the naked eye from Earth at approximately 2.5 million light-years, was the nearest large spiral galaxy to the Milky Way, and the one whose future collision with our galaxy, predicted to occur in approximately 4.5 billion years, was the most specifically dramatic single astronomical event in the solar system's documented future. The collision between the two spirals would not result in the destruction of either, but in a slow gravitational merger spanning hundreds of millions of years, whose outcome would be an elliptical galaxy, the most common product of major galaxy mergers. The specific irony being that the universe's most beautiful and most recognizable galaxy type produced its most different galaxy type when two of them encountered each other. Spiral galaxies are the most scientifically interesting type for studying star formation, since the gas-rich arms were the sites where new stars were actively being born from the collapse of molecular clouds whose density had been elevated by the density waves' passage through them. Hit the like and subscribe button to see more videos like this. Leave a comment on your favorite type of galaxy. Let's get back into the video. Barred spiral galaxy. In a barred spiral galaxy, the spiral arms wind away from an elongated central bar rather than from a spherical central bulge, the bar being a rectangular or oval distribution of stars running through the galaxy's center, with the arms emerging from the bar's ends rather than from the bulge's edges. Barred spiral galaxies are apparently predominant, with surveys showing that up to 2/3 of all spiral galaxies develop a bar, a statistical reality that made the barred spiral the most numerically common form of the spiral galaxy category, and one that gave the barred category a specific additional significance. The Milky Way was a barred spiral. Barred galaxies are designated SB in the Hubble classification system, with the same A, B, C, E subclassification used for normal spirals indicating arm tightness and bulge size. The specific mechanisms that produced the bar structure were the subject of sustained astronomical research, the leading explanation being that bars formed through gravitational instability in the disk when stars' orbital resonances with the galactic rotation pattern aligned in ways that concentrated stellar density into the elongated structure. A 2008 investigation found that only 20% of the spiral galaxies in the distant past possessed bars, compared with about 65% of their local counterparts. The statistical difference communicating that bar formation was a process that occurred over cosmic time rather than being a property that galaxies were born with, the bars developing as the disk matured and the gravitational dynamics settled into stable resonance patterns. The bar structure was not simply an aesthetic difference from the normal spiral. It had specific physical consequences for the galaxy's internal dynamics. The bar acted as a conduit for moving gas from the outer regions of the disk toward the galaxy's center, the specific funneling effect feeding the central black hole at a higher rate than unbarred spirals and potentially triggering more energetic active galactic nucleus activity. The Milky Way's bar was estimated to extend approximately 27,000 light-years from one end to the other, running through the galaxy's center in an orientation that was roughly aligned with the direction from the solar system toward the galactic center. Looking toward the constellation Sagittarius from Earth was looking toward the end of the Milky Way's bar, a specific directional fact that connected the abstract classification of barred spiral galaxy to the specific observational experience of looking at the densest part of the night sky with the naked eye and seeing the thickened band of the Milky Way that was the bar's stellar concentration resolved into individually visible stars by binoculars or telescope. Elliptical galaxy. Elliptical galaxies were the most diverse in size of any galaxy type, ranging from the largest galaxies in the observable universe containing trillions of stars and spanning millions of light-years, down to dwarf ellipticals smaller than many individual star clusters, with the entire range sharing the same fundamental structural properties that defined the category. Ellipticals are spheroidal or slightly elongated systems that consist almost entirely of old stars, with very little interstellar matter. The specific combination of properties being the most important single physical description of what distinguished ellipticals from spirals: no disk, no arms, no significant gas supply, no ongoing star formation, and a stellar population whose red and orange colors communicated that the star formation activity that had produced them had concluded billions of years ago. The Hubble classification for ellipticals used numbers from 0 to 7 to indicate their apparent ellipticity, E0 galaxies being nearly circular in projection, E7 galaxies being the most elongated, with the important caveat that the apparent shape depended on the viewing angle, since a highly elongated E7 galaxy viewed end-on would appear circular and be classified as E0. Elliptical galaxies contain very little gas and dust, and the gas that is present is very hot and diffuse. The hot diffuse gas being not the cold molecular clouds that fueled star formation in spirals, but superheated plasma at millions of degrees, heated by the accumulated energy of billions of stellar explosions over the galaxy's history. The most massive galaxies in the observable universe were ellipticals, giant ellipticals at the centers of rich galaxy clusters that had grown to extraordinary sizes by consuming smaller galaxies through a process called galactic cannibalism, each merger adding the consumed galaxy's stellar population to the growing elliptical's mass while destroying the consumed galaxy's original structure. NGC 5128, also known as Centaurus A, was one of the nearest large elliptical galaxies to Earth at approximately 13 million light-years. Its distinctive dark dust lane cutting across its otherwise smooth elliptical structure being the visual evidence of a recent merger with a spiral galaxy whose dusty disk had been accreted into the elliptical but had not yet been fully incorporated into the smooth stellar distribution that characterized mature ellipticals. The specific mechanism by which spirals became ellipticals through mergers was one of the most important processes in galaxy evolution, the two most common galaxy types being connected by the single most dramatic interaction that galaxies could have with each other, the collision and merger that destroyed the spiral structure and produced the elliptical's characteristic smooth, structureless, star formation-ended form. Lenticular galaxy. Lenticular galaxies were the most specifically intermediate galaxy type, the classification that existed at the intersection of the spiral and the elliptical, combining properties of both types in a configuration whose specific existence communicated that the galaxy classification was not a rigid system of discrete categories, but a continuum whose intermediate forms were as real as its extremes. Lenticular galaxies are a kind of cross between spirals and ellipticals. They have the central bulge and disk common to spiral galaxies, but no arms. And like ellipticals, lenticular galaxies have older stellar populations and little ongoing star formation. The Hubble designation for lenticulars was S0, the 0 indicating the absence of spiral structure, while the S communicated the disk morphology that distinguished them from purely elliptical systems. Scientists have a few theories about how lenticular galaxies evolved. One idea suggests these galaxies are older spirals whose arms have faded, the gas that was required to maintain the density wave, and the active star formation having been exhausted or stripped away, leaving the disk structure intact but the spiral features absent. Another theory proposed that lenticulars form from mergers of spiral galaxies in intermediate mass encounters that were not energetic enough to completely disrupt the disk, but were disruptive enough to destroy the spiral arms. The intermediate collision producing an intermediate galaxy type whose specific properties reflected the specific energy of the encounter that had created it. Environment was the most important single factor in understanding lenticular galaxies. They were found disproportionately in galaxy clusters. The dense environments where galaxy-galaxy interactions and the stripping of interstellar gas by the hot intracluster medium were both most common and most effective. The Virgo cluster and the Coma cluster both contained large lenticular populations. The galaxy-dense environments where the specific processes that transform spirals into lenticulars operated most efficiently. The hot cluster gas physically removing the interstellar medium from infalling spirals in a process called ram pressure stripping that left the stellar disk intact but removed the raw material for future star formation. Irregular galaxy. Irregular galaxies have unusual shapes, like toothpicks, rings, or even little groupings of stars, and they range from dwarf irregular galaxies with 100 million times the Sun's mass to large ones weighing 10 billion solar masses. The specific category communicated through the Hubble classification system's most honest single moment of taxonomic humility. Edwin Hubble classified galaxies that did not have the regular shapes associated with the defined categories into the catch-all bin of an irregular galaxy, and astronomers continued to use his term. The two best-known irregular galaxies were the Large Magellanic Cloud and Small Magellanic Cloud. At a distance of a little more than 160,000 light-years from Earth and among the nearest extragalactic neighbors to the Milky Way, the two Magellanic Clouds were the most studied irregular galaxies in astronomy and the ones whose specific properties had shaped the understanding of the category most directly. Both clouds contained both young population E stars and old population 2 stars. The mixed stellar populations communicating that irregular galaxies were not simply galaxies that had not yet formed spiral structure, but systems whose complex star formation histories reflected the specific turbulent gravitational environments that had produced their irregular morphologies. A large trail of debris from the interaction between the Milky Way and the Small Magellanic Cloud had been strewn across the sky as a series of gas clouds moving at abnormally high velocity, known as the Magellanic Stream. The physical evidence of the ongoing gravitational interaction between the Milky Way's enormous mass and the two small irregulars that orbited it, the stream communicating that the process of gravitational disruption that produced irregular morphology was not a historical event but an ongoing physical interaction whose current effects were directly observable. Astronomers thought these galaxies' odd shapes were sometimes the result of interactions with others, the gravitational disruption of an encounter with a more massive neighbor being the most commonly identified mechanism for converting a previously regular galaxy into an irregular one. Dwarf galaxy. Dwarf ellipticals are probably the most common type of galaxy in the nearby universe, the specific statistical reality being that the universe's most common individual entities were the ones that individual human observers were least likely to notice. The dwarf galaxies being too small and too faint for casual naked eye observation, but sufficiently numerous to constitute the majority of the galaxy population in any given volume of space. Dwarf galaxies ranged in mass from several million solar masses to 1 billion solar masses, a range that made the largest dwarfs comparable to the smallest normal galaxies, the classification being a continuum of size and luminosity rather than a sharp boundary. M32 was a dwarf elliptical galaxy and one of the companions to the giant Andromeda galaxy M31. Only 2,400 light-years across by galactic standards, a compact system whose small size was described as dwarfism relative to its neighbor's enormous 220,000 light-year diameter. The Milky Way had numerous dwarf satellite galaxies, the Magellanic Clouds being the largest and most famous, but dozens of smaller dwarf spheroidals and dwarf irregulars orbiting the Milky Way at various distances, some so diffuse that their stellar density was barely distinguishable from the background of more distant objects. Dwarf galaxies were cosmologically significant beyond their individual properties because they were the building blocks of larger galaxies in the hierarchical model of galaxy formation, the model in which large galaxies grew by accreting and merging with smaller ones over cosmic time, the Milky Way having consumed numerous dwarf galaxies across its history, with the Sagittarius dwarf galaxy being the most actively studied current example of a dwarf galaxy in the process of being disrupted and incorporated into the Milky Way's stellar halo. Ring and interacting galaxy. Ring galaxies and interacting galaxies were the types that communicated most viscerally what happened when the universe's largest structures encountered each other. The category whose existence proved that no galaxy existed in complete isolation from the gravitational influence of its neighbors. Ring galaxies formed when a smaller galaxy passed directly through the center of a larger disk galaxy, the impacting galaxy's passage sending a density wave rippling outward from the impact point like a stone dropped into a pond, the expanding ring of star formation being the visual expression of that density wave compressing gas into the conditions required for star formation as it propagated through the disk. The Cartwheel Galaxy at 500 million light-years from Earth was the most famous ring galaxy, a system whose bullseye structure of an inner ring, outer ring, and spoke-like connections communicated the specific physics of a nearly perpendicular collision that had sent the star formation wave expanding uniformly outward from the impact site. Peculiar or interacting galaxies were those whose appearances had been dramatically altered by collisions or internal instabilities. They often showed extended tidal tails, intense star-forming regions, and compact young star clusters whose formation had been triggered by the compression of interstellar gas during the encounter. The antennae galaxies NGC 4038 and NGC 4039 were a nearby iconic merger with widespread star formation and dozens of young massive clusters. Their 2-bay-long tidal tails extending away from the collision site, communicating the specific gravitational dynamics of two spiral galaxies whose encounter had disrupted both disks and pulled stellar material into the characteristic antenna shapes that had given the system its name. The Mice galaxies provided spectacular examples of long tidal tails produced by a close encounter. The two systems extended streamers communicating that galaxy interactions did not require direct collision to produce dramatic structural changes, gravitational perturbation during a close passage being sufficient to pull vast quantities of stellar material out of the disk and into intergalactic space.